Okay, so I want to talk about underwater robotics. I've been in this field for approximately 12 years now. So after studying at the University of Oldenburg, I did a master there in embedded systems and microrobotics. I went to the German Research Center for Artificial Intelligence, just around the corner here, the Robotics Innovation Center, and did my PhD there for tactile sensing for deep sea applications, so in 6,000 meters in depth. And afterwards, I went to industry, and that's where I am now, still in Bremen-Hemelingen, so one of the quarters of the city. We are directly located near the river. And what you're seeing here in this image is one of the photos taken from our field trials that we are doing with our underwater robots. What you can, I don't know if you have already spotted the vehicle, so it's located here. This whole picture was taken in the North Sea, very clear water in these environments, so yeah, up to 5-10 meters you can still see your robot, which is nice for many people because they want to see what the robot is doing and want to directly see the reactions to the commands or the autonomy behavior. But that's one of the challenges for underwater robotics. In normal cases, you just let the robot go and then it's off and you don't see it anymore. And on the one side, this is the most relaxing part because you can't do anything anymore. It's just away and you can just pray that everything works to plan. But on the other side, of course, you're worried that it will come back as these robots are very expensive, several million euros. Of course, you have to be sure that everything works according to plan. Yeah, and with these introductory words, I would like to welcome you to the underwater world to actually show what it's all about, how underwater robotics works, and yeah, what are the challenges, and perhaps give you some kind of ideas what AI, artificial intelligence, machine learning in general can do for the underwater world, and want to motivate you to look into that field and yeah, perhaps help us underwater robotics guys to overcome some of the problems we're actually facing. So what you're seeing here is a typical situation that you face when you are trying to operate underwater robots. You have your ship at the sea surface, you have a crane at the back, should be depicted by this yellow stuff here at the ending, and you normally are facing the first challenge already. You have your vehicle, your ship that's on the water surface, you have the waves, and you start to lift your robot, and the mass of the robot already starts shaking, and you need to make sure that the robot does not crash into the crane or into the ship. And if you are lucky enough and this works, and you're trying to submerge the robot into the water, you have another problem. You have the damping of the water, the robot being still attached to the crane, and you need to, again, make sure that your robot does not crash into the ship. So what you're normally doing is you're directly moving this thing into the water and immediately detach the robot and try to get as far away as possible with your robot from the ship in order to make sure that the robot stays safe and your ship stays safe as well. And that's why in many pictures, and you see this here as well, the sea conditions are very calm. When you're looking at marine robotic images, always the sea is flat. And that's, of course, something that's not desirable because you want to go with your robot into the ocean anytime. And that's one of the first challenges. So if you want to work with a crane manufacturer or somebody else, it might be something you can try to work on. And if you're on the water surface and you're trying to start the mission, you're facing the additional challenges. Normally you have some kind of antennas here in the upper part, so this area normally is covered with LTE, Wi-Fi, Iridium, whatever you're finding for communication, perhaps Starlink as well sometimes, and you're trying to communicate with your robot. And then another challenge comes up. The waves, what we are talking about already, if they are splashing over these antennas, you lose your connection. And yeah, you need to make sure that your robot actually gets the command to start the mission, or you have some kind of timeout, and this whole robot starts moving. And if you're going to dive in some kind of areas near your ship, you're facing the next challenges. You're immediately losing connection regarding your radio frequencies. So Wi-Fi, LTE, all the stuff does not work anymore. And the same holds also for your global satellite navigation system. So all GPS and the stuff as well is out of function. So what you have to do is you try to have some kind of initial position, and from that you're using the onboard sensors in order to navigate and find out where you're actually going. This has another challenges. We will talk about this later. Then you're going to dive in some areas where the seafloor is far away from the surface, so talking about several hundred meters. This already is enough. You even can't detect the seafloor with your sonar technology, for instance, that you have incorporated in your vehicle. And you need to make sure that you're keeping the position somehow, or at least know how far you're drifting in the water column to make sure that you still keep your idea of where you are actually on the Earth. And then approaching the seafloor, you're trying to search for the obstacles or the objects you want to track. In our case, I will talk about this later, this is mostly critical infrastructure from the energy sector, so it might be offshore wind turbine installations, oil and gas pipelines, cable networks and stuff like that. And then you're trying to follow that. And of course, this can be buried sometimes, you can lose the connection and you need to find that again. And this is the whole situation that you're actually facing when you're designing missions for underwater robots. That's the general picture that we are facing. And to give you a little bit of an introduction, what actually is an underwater robot about, I want to talk about these key topics that I have placed here around this yellow thing in the middle, which should be some kind of sketch of an underwater robot. So mostly when we are talking about underwater robots, we're talking about completely autonomous underwater robots, which are abbreviated by AUV. So AUV stands for Autonomous Underwater Vehicle, and that's the thing we are seeing here on the picture. This means that we don't have any cable connection to the ship, to the surface somehow. There are other vehicles available that are more like a remote-controlled toy car, so these are remotely operated vehicles where you actually can see all the time what your vehicle is seeing, what is experiencing kind of depths and other situations. And the key parts, components that are needed for such kind of a vehicle, starting with the propulsion stuff, is that you have active thrusters, motors that are driving your vehicle around. You have them for the forward motion, sideboards, rotation on the spot, and diving as well. And you can separate that into rudders, so if you want to have some more energy-efficient approach on that side, or you're using buoyancy cells in order to go up and down. So these are the two possibilities. Buoyancy is another important key part for this whole thing. As normally you're designing your shape of the vehicle, you have normally metal material that you use as a structure, you have pressure hulls where your electronics is in, and you need to withstand the ambient pressure, for instance. And in many cases, titanium is used for that. And this is mostly due to the reason that, again, mixing different kind of materials, metals especially, leads to corrosion rust on the vehicle itself, of course, which is something that you don't want to have because of the interaction between these different kind of materials. One of them becomes the so-called sacrifice anode. So that's why, of course, you have a negative buoyancy using this kind of materials. You need some kind of buoyancy foam to get the vehicle back up, or at least to stay buoyantly neutral. And this is another part that needs to be taken into account. If you have seen such kind of vehicles already and you're wondering what this yellow part is on most of these vehicles, so this is mostly this buoyancy foam we are talking about here right now. This is mostly colored in that kind of shape, especially in order to find it back when you're on the ocean and try to cover large sea areas to find this vehicle. Yellow is a good contrast to the watercolor. Communication, I already talked about that. You heard about the challenges we are facing here. It's not that we are not able to communicate at all when the vehicle is submerged. There's acoustics available. This will bring you back into ancient times of the first modems. Some kilobits is the data rate that you can use to transfer data. So talking about image transmission, just forget about it. That will take days in order to be able to get that. Then, of course, we have the ambient pressure. I already talked about that. So you need to cover your whole electronics and stuff into housings normally. There are pressure-neutral approaches as well, where you try to find the right electronic parts that actually survive the ambient pressure. And as I said, you have the localization issue, and yeah, you just need onboard sensors of a high quality. So talking about fiber optic gyros, for instance, and accelerometers of high quality, DVLs, so Doppler velocity log, trying to acoustically locate you on the seafloor as well. And of course, all these kind of technologies I was just talking about are not for the only for the sake of keeping the vehicle in a safe state, but you also want to do something with it, right? You want to sense the environment, and of course you need a lot of sensors for the environment perception as well. But still, if you're already deploying your vehicle and you say, okay, there should be everything ready to get my technology running now. So what I want to talk to you about here is the topic of light, absorption of light. I don't know if anyone has already exactly. It's like that. You can just use this kind of picture, but it's not dark and black. At the end, it's black again, of course, for sure, because we are losing the ambient light from the water surface as well. But I don't know if you have experienced that already. If you have colored objects in the water and you're moving away from them, sooner or later they're becoming blue, because all the other wavelengths are absorbed quite early in the watercolor, and that's why it looks like that. Is there a question? Okay. Yeah. Okay. All right. And that's an issue for sure, because if you want to say, okay, I want to implement some kind of autonomy and try to realize this kind of stuff, you can forget about using colors for object tracking, because your colors fade away, and you need to find another idea, or you bring your light with you, of course, that's possible, and then you need to take into account that, of course, only in the vicinity of your light source, the colors will stay in the way you actually want to have them. So talking about autonomy there, yeah, it faces a challenge, or it is a challenge, and that could have been seen in this picture, or these images. But nevertheless, I think you get the idea of yeah, getting this fading away. And blue is the last color that actually stays. Another video was in here. Might be that this works, but nonetheless, material stress is something else. I think it's also pictured here in some kind of excerpts from Twitter. That is that, of course, we are not alone in the ocean, and there are other, especially animals around. And they are interested in your vehicle, for instance, and they are trying to taste how your vehicle yeah, tastes. And you see this, for instance, here. This was the original state, and this is the state afterwards. You might see the shark here around. So there are sharks that actually attacking AUVs, underwater robots. And I don't know if some sailors are here among us. There's actually a problem that sailboats are attacked by sharks in the entry of Gibraltar, so in the Mediterranean. So they are chewing your rudder, which is a problem, losing your rudder on a sailing ship. And of course, this is the more exotic material stress that you might not be having taken into account already. But of course, there's the obvious one. So going into harsh environments like a storm, for instance, like the sail drone, which is a surface vehicle, is actually facing. These are other situations that you might face. And of course, the same holds for underwater as well, as you're having currents and waves acting on your vehicle. And you need to make sure that you're withstanding that. But that's more a material issue, perhaps not the issue for autonomy in itself. Yeah, but what makes it still interesting, or additionally interesting, is of course what I said. We have this camera issue that we also, if we are down there, there's not much contrast in the stuff you're actually facing. So you see there a pipeline on the seafloor. It's a grayscale image, obviously, and you see, okay, there's not much difference between the seafloor and the environment. And what we are quite often using is some kind of sonar data. So this is an imaging sonar data that you're actually seeing here. And it needs some kind of creativity, fantasy to actually see what's on that picture. So what you can see there is a basin, a test basin within a test facility. And this quite often has some kind of ambiguous possibilities how to interpret these kind of data, especially when it comes to automatic interpretation of these kind of technology. And this, of course, makes it also quite interesting. Also, so what you're normally trying to face here is some kind of obstacles, structures within the sea that you want to monitor closely, where perhaps your image data is not available. And for instance, you're also using this kind of technology actually to avoid obstacles. So you don't want to crash into structures. But as with lots of other sensors, you're also experiencing false positives here as well. So if you're trying to scan the environment, it might be that just to a change of the density or salinity of your water, you might observe already obstacles that can be seen by this kind of sonar data. And of course, that's something you don't want to go around. It's not an obstacle, but it's actually visible in your data, and it can be misinterpreted as well in that regard. Localization, I was talking about that for quite some time already, so GPS doesn't work. We have these kind of black boxes here. These are fiber optic gyros for the 3 degrees of freedom for the rotational part. And you're using this kind of technology. It's called the Doppler velocity lock. So it's exerting sonar pulses on these 4 piezo transducers to the seafloor, and you're measuring the runtime and the difference between the runtime, and you're getting the extra travel over the seafloor, as long as the seafloor is within the reach of these kind of sensors. And then you combine this with a pressure sensor, and then you have your environmental data that you use. But as you might know, there's drift available in these kind of accelerometers, gyroscopes as well. So if you're thinking you're going straight, you're actually drifting apart. That's something you need to take into account, especially if you're traveling larger distances. And that's, of course, something we need to do. But in the end, that's something we want to achieve. And of course, that's achievable. So there's technology outside that does this, where you actually can map the seafloor, get this combination of sonar data. For instance, you have a point cloud there, and you're putting on top image data, and then you get this coherent image as you're seeing that there at the top. Okay, I was talking a lot about challenges, problems, what makes it so difficult. And you could also say, okay, why is localization such a problem? Why don't you just take some kind of map like you have when you want to go from A to B in a city? Yeah, there are no maps. So that's something that is also quite surprising. Detailed maps do not exist. There are actually more detailed maps on the Moon or Mars than on the ocean seafloor. And there's an initiative like the Seabed 2030, and they are trying to map 100% of the ocean floor by 2030. But mapping means, we have to ask about the resolution, right? So if we are traveling just on the water surface and we have depths of 4,000 to 6,000 meters, what kind of resolution have we down there? Because that's the one we need when we are going with AUVs, because mostly the seafloor is interesting. Water column is mostly not that of interest. Might be interesting especially for marine environment scientists, but for the industry area, of course, the seafloor is the more interesting part. And there you see the percentage of resolution that we are talking about. So on the 1 to 1,500 meters, it's only 13%, and even less if you're going deeper, as it is shown here. And yeah, the current state is 23.4% is actually mapped. So the rest is still unknown, which of course is interesting for us because it adds up to the challenge of autonomy, but yeah, doesn't make our life easier. And with that part, I want to come to some kind of ideas, some kind of motivational parts, how we can actually tackle or try to find something. As I was talking about this mapping or having these imagination of how the seafloor might be looking like if we have a robot down there, we might be using some kind of approach from the machine learning area where we try to map this these cartography data from the water level to the actually position of the robot in the end. So using some kind of approaches like generative adversarial networks that we can use, okay, say we have the data from the water level, how might this be looking like if we are approaching the same area from another perspective, meaning having the robot just approaching this several meters above the seafloor. So this is one of the ideas that might be interesting and might be something to think about. Of course, that gives us not additional maps or higher resolution, but it gives us more like a model that we need for autonomy in order to be able to anticipate what we might be experiencing. And that's also very interesting, of course, for robots in order to pre-train them towards their mission. I talked already about colors, about color loss. So this would be a typical image that you could get from a camera, from a diver that's going around. And there's a lot of algorithms existing that try to enhance these kind of images, try to get the original color distribution back. And there are also papers available. I'm just citing one of those here. You will find a lot of those in the literature where they actually try to get back the original color distribution. And there are measures available like colorfulness, so the distribution about the whole color scheme, the sharpness of the image, the contrast, and these kind of metrics are used in order to try to re-establish the original idea of the color distribution that we are observing when we are trying to capture these environments with cameras. Another interesting part might be vehicle controllers. So as we are talking about AUVs, normally they do not stay in the same structure like they have when we are actually assembling them. So what might be interesting is rearranging sensors, for instance, which results in a change of distribution of mass within the robot. And of course, this means that your whole controller module that you have designed is not valid anymore because the mass distribution have changed, your vehicle parameters have changed, your thrusters in order to propel the vehicle need to be adapted. And of course, that's something you would like to automate somehow. So it's very nasty and time-consuming to redesign these kind of controllers because you need to adapt the vehicle controller module. And there are also some kind of approaches there as well. So here's a paper from using deep reinforcement learning to actually reestablish the connection between what you're observing and your controller data to find out, okay, how can I actually control the vehicle and how can I adapt the technology that I have in order to propel my vehicle around. Another interesting area is the positioning of the system itself. As I was telling you, okay, we are talking about IMUs, fiber optic gyros, DVL data. And of course, there is also a vehicle model behind that in order to fuse this kind of information. And this is mostly done with so-called Kampmann filters. And also they need some kind of vehicle model. So you need some kind of system behavior incorporated there as well. And there are also existing approaches where you could use neural networks in that case in order to try to adapt to this changing vehicle models. And this might be also an interesting application, an idea how we actually can use machine learning in order to support this kind of technology, especially in the navigation area. Yeah, one of the last parts I want to show is, of course, I think a very easy and obvious part is classification of the environment using image data, sonar data in order to actually find out what you are seeing. This is especially interested in the marine biology environment because, of course, they want to try to identify as much of the objects of the animals, of the stuff around, and need to cartograph the distribution, for instance, stuff like that. And that's a very time-consuming task because in most cases this is done by hand. So there are a lot of students around trying to label, okay, this is the kind of stuff I'm seeing here and there. And there are the first networks, which is, this one is the FeatherNet. I'm giving you more data about that in the next slide, where they actually try to automate this kind of stuff. And this is perhaps surprising, but this is just happening now. So there have been a lot of people spending a lot of time in front of the screen to manually label this kind of stuff. yeah, and of course for the more industrial approach here, we have this paper there where they use this you only learn once networks for detecting submarine cables, for instance. Yeah, as always, this whole stuff is always about data in order to train this whole stuff. And of course, that's the problem. As I said, only 23.4% mapped, so there's not much data available. That's another problem. But there are data sets, and yeah, I'm just having 3 screenshots here that show you actually where you can go more in depth to find some kind of initial starts to train networks if you actually want to try this out and try to support this whole underwater robotics area with some additional technology to make this life easier. Yeah, some last words. If this is interesting for you, I have never talked about where I'm actually working, so that's the Rosen Group. We are distributed all over the world. Our main tasks are to do inspection tasks in offering services to companies in these environments where we are talking about safety critical infrastructure, being this onshore or on land. And we have so-called Rosen Technology and Research Centers. So this is the area where we're actually developing stuff. They are also distributed all over the world. There's one in Bremen, that's where I'm from. And yeah, if you're interested in this kind of stuff, feel free to contact us and join us and support us. Thank you very much. Yes.
Any questions? Okay. I will start with Arthur.
I
Hello,
thought you were
good
throwing
morning.
that.
Is this working? Yes, it is. Hi. You will probably have some unforeseen situations with that submarine down at the bottom of the sea, and you can't control it by yourself because you're out of reach. So how do you do failure handling and reacting to these things?
Yeah. That's, of course, a very big topic for us. And yeah, we are trying to face that in different approaches. So for once, what we are doing at first is making sure that this vehicle stays safe all the time, because that's precious and we want to get it back to the surface. So that's the first and major condition that we have. And the worst case for us is, of course, losing this vehicle and not getting it back at all. And of course, there are several issues that we can face. So you could have a water ingress, which is, of course, very severe. It means normally direct mission aboard, and you're trying to get the vehicle on the surface as fast as possible. So this is the most obvious one, and the one that's the most critical. But there are other solutions or situations that you, for instance, having a sensor that does not react anymore. You're running out of battery, you're not reaching your mission in the end, and stuff like that. And all this kind of stuff that we at least can think about at the beginning, we are trying to have some kind of countermeasures. So having, for instance, losing a sensor connection, we are constantly monitoring the power consumption of each sensor. So we have current meters for each sensor there. We have an anticipated model of what kind of power each sensor should consume. And we can see, okay, is this in the foreseen area, or is this somehow moving into a direction where we're consuming, for instance, more or nothing at all? And therefore we have programmable fuses that we can switch on and off and try to restart the components that we have in there. We can remap the propulsion system. So we have, in our situation currently, we have 6 thrusters, 2 at the back, 2 at the side, 2 at the top. So to dive, we have 2 thrusters. To turn on the spot, we have several combinations that we can use. We can just use the thrusters at the back, moving one forward, one backwards, so have a differential approach. We can turn on the spot. And all this allows us to readapt. So if we are losing one of the thrusters, we can change and try to adapt and use, okay, we have another situation where we can use these kind of thrusters. If we have software components that are not running, we have some kind of supervision technology. So we're using the robot operating system, ROS. And we have designed a base class for all these kind of nodes that we are using, which is the state machine. So in ROS 2, that's already there. There's this life cycle management, and we did this for ROS 1 as well. And we have some kind of technology that makes sure that all these components stay in the right state, and we can re-switch them to the states that we actually need them. There's also load balancing included in that, because you also don't need all nodes running in parallel. And just to give you a figure about that, we have 70 nodes running in parallel. 70, not 17, 70. Yes. So it's really a large ROS network in that case. And yeah, I could go on on that area. So there's a lot of stuff there. But of course, and that's also the more interesting part in terms of challenges, we also have these conditions we do not anticipate before, right? We do not know what we are experiencing in some cases. And we are trying to overcome this by having really extensive simulation where we not optimizing towards one world, where we're changing the worlds constantly and in the best case automatically as well, in order to find out if there are corner cases which you do not have experienced yet or haven't thought about.
Cool. Thanks.
Yep.
Okay, thank you very much for the presentation. So to bringing also robot kinds of outdoors. So my question was a bit about anticipation, as you just mentioned. You saw how we struggle with sensor, with technologies. So if you see AI from a functionalist kinds of point of view, that, okay, my problem would be just to map the input and the output, no matter how I do it. So history show us that we are like wrong, so that we should not just go like this, trying to map no matter how we do it. We might have to observe how humans do this or solve the problem and try to inject this into our robots. So I listened to your presentation, so I'd like to know whether or not, or what insight you got already from human cognitions, or what did you get from it that you could say, okay, I got it and I have to inject it. I have like these cognitions kind of enable underwater robot. Yes, so I will not jump into the area of perception to say, okay, you told us how it is difficult to perceive with those sensors. For example, I'm not a perfect swimmer, but when I get into water, I have most of the time my eyes closed. How do I get to achieve my goal to move from one point to another point, something like this? Thank you.
Yeah, okay, thank you. If I understand correctly, your question is, what kind of human behavior that we are observing can we incorporate in the modeling of the autonomous behavior? Is that correct?
Yes, that allow the robot actually to overcome all those technology issues.
Yes, okay. Yeah, that's a very interesting part, because I'd say in many cases the world where we are going is not made for humans, because we are underwater and we are using sensor technology that cannot be mapped to the ones that humans have. So of course vision would be very easy, because that's what we have, and we can say, okay, we compare cameras to human vision, which is dangerous in itself, because that's not the same technology and they behave differently. But sonar technology is not something we can use as humans, right? And that makes it a little bit dangerous, in my perspective, to transfer the idea of how would a human behave going from A to B and transferring this to an underwater robot. I think.
If you don't consider, for example, human, they are at least, biological agents, so that are able to exercise and so.
Yeah, I think what would be more nearer to that is looking at animals trying to move around. So like sharks or other animals that have some kind of sensor technology that surprisingly allows them to navigate underwater pretty precise. So there are animals around that can travel through the whole ocean and directly approach, for instance, an island, or they are able to find Australia with a very high precision. Of course, that's not that small, but anyways, if you're constantly underwater, there's an easy way to just miss it. And this is kind of the sensing technology we are actually looking into and the processing technology. And there's, of course, a lot of inspiration from bionics that we are trying to use and try to incorporate. And there's a lot of work on that. But I think where your idea of human behavior more comes into play or could be used is in the whole system management of such kind of a vehicle. As I was telling, we have 70 ROS nodes, and of course, having them all talking with each other is a nightmare on the processing side. So what we are doing many times is comparing these kind of architecture we use in order to operate the whole autonomy level, is comparing it to a company structure. So you have divisions and departments, and you have some kind of managers, and they are talking to each other, and you're trying to abstract. And that's something that's very important, that you're trying to invert abstraction in this whole design in order to reduce the complexity. And that's, I think, something we try to take over in this regard.
Yeah, just let me take the last point. Regarding sensor for, because like you're arguing that maybe animals have like a sensor that allows us to, as we might also always claim that we have a sensor, but we are saying that we are not always using those sensors, kind of. So don't you maybe think that animals also have like this anticipation power that allow them also sometimes to get without kind of sensor or something like this?
Oh, absolutely. I assume that, but I think we have to look into literature to actually see what's there. And to be honest, I don't have the overview in that regard. But I'm pretty sure that there will be something there. Yeah, you're right.
Yeah, thanks for the nice presentation. In the middle, you said that you use like SLAM-like technology to locate in the underwater environment. From my experience, that doesn't work because seafloor is not really full of landmarks that you can navigate around. How are you doing that?
Where did you
see the big tube in the navigation?
This one?
No, bigger tube.
Bigger tube.
Yeah, that one.
Yes.
Yeah, because these tubes are not everywhere.
No, absolutely right. Yeah. It just depends what you want to do, right? If you want to navigate based on landmarks, you need to go where landmarks are. That's true. And a lot of the part of the ocean seafloor is only sparsely covered with some kind of structures. And that's not useful at all. You're right. Nonetheless, this is still used. So there is SLAM approaches based on stereo cameras, for instance, where they actually try to use this kind of, even this very sparse structures that we have. But I think you need to distinguish between the idea of creating a map and the idea of inspecting something. If you're going to create a map, you don't need to localize using landmarks. You're using just the onboard sensors like these fiber optic gyros, and you're traveling across waypoints that you have predefined. Oh, okay. And normally you have some kind of lawnmower pattern where you're going up and down, and you're having an overlap where you can try to realign your sensor data based on this overlap in order to compensate for the drift. And in the post-processing, you're generating the map. Mm-hmm. This is one of the ideas of using underwater robots. The other approach is where you actually have these kind of structures. So we are in an industrial environment, industrial context, where there are pipes, where there are structures, where there are anchor chains, where there are cables, and you're going to track them. And then you're using this, but mostly you're using environment sensors to being able to track it, and then let your onboard sensors for the positioning run in parallel. And afterwards, in the post-processing, you're remapping this to the precise locations that you anticipate.
Okay, thank you.
Hi, thanks for the nice talk. You mentioned some things that made me think. So you mentioned, for example, that the sharks sometimes attack the underwater robots. And you're using, for example, a propulsion system. Sonar also works with sound waves, right? So you're emitting a lot of noise that could attract sharks or disturb other animals. Do you take any measurements or any countermeasures to reduce the noise level?
Yes. So in general, of course, if you're using electric propulsion, you are not able to reduce that to some kind of extent. But anyways, as you're looking from another perspective, you want to be energy efficient on that side. And that's why you're not mostly relying on electric motors, but using more rudders and have them just very rarely change their direction in order to be as energy efficient as possible in that regard. So that reduces the noise of electric motors. You're having sonars, yeah, that's true. But there's some, so of course they're exerting noise, but compared to something that's on the water level, you need much less noise emission in order to create your data than compared to something that's on the water level. It's very easy. If you're on the water level, you are going through all the water column, which is not interesting for you, but you just want to reach the floor, but you need more power to actually get there with your sound wave. If you're using your underwater robot, you are just 4 to 5 meters across the seafloor, and you're much more silent already with that. And then, of course, it's also a matter of frequency, so how often you're actually exerting your noise, and this also can be handled. But yeah, this is, of course, one of the issues that might be attracting these kind of animals, and this might be one of the issues, yeah.
Okay, thanks.
My question would be, how do you plan the like a mission, you know? So you have this vehicle, and then I don't know. I think you have different scenarios. So if you want to explore, like you don't even know what's there. So how do you plan where the vehicle is supposed to go?
That's a very good question. And again, it depends a little bit what your idea is. And of course, I think you're already assuming that there are various approaches. And the easiest one, and that's the most commonly used one, is you are just mapping something. So you're generating this lawnmower pattern I was talking about, going up and down, and you have predefined waypoints. And you're just telling, okay, this is your starting point, there you're going to dive, and then you're following this kind of track. And that's the very easiest approach because you don't need to rely on any external senses, external perceiving data, because you're just collecting data and you're moving across these waypoints, and you track your position using the onboard sensor data that you have. The other one is a little bit more challenging, and that's the more interesting part, is where you're actually trying to track something, where you want to find something on the seafloor and want to move along that. And what you're normally doing there is you're defining some kind of starting area, and you again have this lawnmower pattern I was talking about, where you try to search for that object you want to track. But as soon as you have found that, you're of course in some kind of autonomy mode, directly reacting to what you see. And perhaps you have a model already incorporated, some a priori knowledge, where you say, okay, I'm anticipating this is moving in this kind of direction and turning and this like and that. Or if that is not available, you're purely on your sensor data. And that's what happens most of the time. And then you're having difficulties, of course, predefining your mission end, for instance. So when is this object not visible anymore, when you have completely covered your track? And you have several possibilities there. You're just saying, okay, after a certain amount of time, I'm trying to finish my mission. Or you say, okay, the first time I'm losing track of the object that I have, I'm going back to the surface or going to a safe parking positions, for instance, and wait for some additional command to get back to a ship, for instance, that covers or brings the vehicle back. Yeah, these are the two possibilities you mostly have.
Thank you very much.
When it comes to
You have to use it.
you spoke kind of made a lot of mention to the power consumption and efficiency. Like, can you comment a little about what's the power consumption in total of the system, how in standard operating conditions, how will you where is the most load, how do you handle that, and like how long does a regular mission last, how much of an autonomy you actually have in terms of a standard mission.
Yeah, also very interesting point and very crucial point for the whole idea. So the main power consumption normally is coming from the propulsion element. So the thrusters are consuming the most power. Afterwards, it's mostly the onboard communication and then the sensors. And for the thrusters, we are talking about 500 watt to 1 kilowatt. For the internal stuff, we are talking about 200 to 300 watts, depending on the amount of PCs you have, depending on the amount of number crunching you're doing online. And then you have the sensor data for 200, 300 watts, depending on also, again, on the sensor technology you're using, the frequency you're having, and stuff like that. And mission length is of course much depending again about the amount of batteries you're taking with you. So currently I think there's as this development of electric cars is doing a lot of pressure on the battery development. There's a lot happening also for the battery development for underwater robots. So we are talking about kilowatt hours up to 100 kilowatts or more. And again, depending then on your frequency you're trying to collect data, there are research institutes, for instance, the NOC in Southampton, National Oceanographic Center. They are having missions of up to 2,000 kilometers, for instance, and they are traveling for days. But yeah, of course, there's also the lower end, depending on how much battery you're consuming. It could be also that you're just working for 8 to 12 hours.
So this is a petrol power source?
No, it's electric.
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 Okay.
There's only electric and hydrogen. These are the two power sources you have for underwater robots.
Okay. Thanks.
Yep.
Yeah, thank you for the great talk. You mentioned something about the effort trying to map the entire seabed by 2030, right? And if I understood you right, that would help localizing robots underwater. So how much sense does it make, in your opinion, to map everything? Because I can imagine like seabed areas where they undergo constant changes. For example, like mapping the desert doesn't make a lot of sense because the dunes are shifting all the time. So if you have a map now and then a couple of years later it looks completely different, how would you face these challenges, or what are you planning?
Yeah, good point. Especially, so we are directly here in an area where the seafloor is constantly moving. So the North Sea has a lot of currents on the seafloor, and this is constantly changing. And there need to be a lot of updates even for the navigational maps for ships. And of course, this is a challenge. And of course, this could only mean that you constantly need to go there and remap if you actually want to have data from that, or you're trying to survive with the uncertainty and trying to work there as well, which is happening already right now, right? So we are able to face that and compensate for that. But of course, it's easier to have some kind of pre-knowledge, inserting that in your autonomy, have a model where you can try to see, okay, I'm observing these and these kind of conditions, what can I do? And it might be that these areas perhaps are not the first I would put the most effort in trying to remap them all the time. I think the biggest challenge is just to have generally a map already. And I think it will happen a lot with ships using multi-beam echo sounder data, so in some kind of acoustic line laser and trying to map the seafloor. And and just hoping that this will happen actually to 2030. And of course, then the question will be about the resolution that we can use for that, and if it's actually helpful for robots to navigate and relocate based on map data, relocalize.
Okay, any further questions?
Thank you for the talk. It was very interesting. I'm curious on, so for industries that can, like for deep sea drilling and offshore energy and those sorts of things, where they sort of know what the structure is that's going to be on the seafloor, is there a lot of effort to design those actual like infrastructures so that they are easily detectable by the robot? So there's one picture of the cable I saw that had like kind of those like colored lines across it.
Yeah.
Is that common in the industry to have that? Or?
Yeah, also very good question. Actually not, no, because interestingly enough, many of the companies that operate these kind of structures or they're designing these structures are led by former divers. And they are transferring technology that they have used while being a diver just to higher depth. And most of the structure are more made for human intervention than for robot interaction. And that's a problem, yeah. But there are companies and startups growing that actually directly approach the idea you're having. So there's, for instance, a company in France where they want to put some kind of QR codes. So officially, these are Aruko markers. These are more easily handleable by robots in order to being able to localize yourself again on objects that are on the seafloor. So they are placing this marker. They are measuring with GPS where they actually laying this on the seafloor. And if your robot is approaching this marker, you directly know where this is on a global scale. So this is happening. And there's an upcoming invention of underwater docking stations, so talking about recharging stations for underwater robots, like a petrol station for cars. You have them distributed near your structures, and you are able to, getting recharged in a standardized interface, and also to being able to transfer data inductively, so like on your toothbrush, for instance. So this is happening, but it's just coming up.
Could I ask one follow-up? Or I also noticed from the examples that you showed, the robot is always sort of passively sensing, or at least is constrained to sort of sensing the environment. Are there visions to eventually have the robot actually manipulate the environment in some way, or like manipulate the infrastructure that it's sensing?
Yeah, also very interesting point. That's actually also part of research, to have robots with manipulators doing intervention. This is already happening with remotely operated vehicles, so where you have the cable attached to the ship, you have controllers where you can use manipulator arms moving them around. For autonomous underwater robots, that's very challenging because normally you don't have the power on these kind of vehicles. You're mostly powered on an electricity that's on board. And you need to exert some kind of counterforces, right? If you're trying to manipulate an object and that's very strongly connected to something else, there's even the danger of moving the vehicle around than actually moving the stuff you want to manipulate. And that's one of the things that are a problem here. And of course, having changing mass distribution. So if you're trying to grab something, collect something, your mass distribution is now completely different than before, and you need to readapt your model in order to operate this safely. And there's sensor technology, so normally you want to have some kind of feedback if you're grasping something. That was my PhD about, so I worked a little bit about this, but this is extended to manipulator arm as well, where you need some kind of force interaction. So there's a lot of stuff and potential for research. But that's actually something that will come up, yeah.
Thank you.
So if there are no further questions, we can go and have an extended break. Thank you very much.
Yep.